find how what is the ideal size, the exact size of the pixel, and there is a example we have already done. You see here, this is a question, and if the physical size we have already discussed. Uh, this is a uh, 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 questions. I have already discussed what is the ideal size, and the ideal size is according to this theorem is greater than or equal to 2 into f max, where f max is the highest frequency present in the image, or otherwise the original signal cannot be reconstructed. We had a example, you see in the your screen. What should be the physical size of 2D image of a document with dimension 2400 and 2400 pixels when scanned at 300 dpi. So according to rule, the physical size of the image is number of pixel by resolution. So you will get that is the image size is 8 inch into 8 inch. So that means the physical size of the image should be 8 inch or into 8 inch. Otherwise, it cannot be uh, uh, a good image. So if the physical size of the image is 8 into 8 inch and sampling resolution 5 cycle it is given that. And an additional question is how many pixels per cycle are required to have the better quality. And another additional question is there: will an image of size 256 and 256 be enough? So if the 5 cycle per meme, therefore for better quality 2 pixel per cycle are required, and because it is 2 into f max, so it is 10 pixels. So you see, it will be noted that is, we know that 1 inch is approximately 2.5 per centimeter. So 8 into 2.54 into 8 into 2.54, 20.32 square centimeter. When we convert it to pixel, that is 2032 into 2032. So minimum required of pixel is 2032 and 2032 pixels. So the image of size 256 and 256 is not enough. So the answer of the additional question is that the image of size 256 cross 256 is not enough. So this is your pixelation error. So if you will get a question, what is the short note pixelation error, write the definition, and if possible, write the example. I have already sent the PPT to your group. Please refer it, and you will get the question, answer, and as well as the examples. Then the another term, image resolution, which is associated with the image quality. That is image resolution. You see, image resolution is higher. That is, if the image resolution is higher, you will get a bright picture. Or that is, the resolution means more image details. In digital imaging, the resolution is often measured as pixel count. So the it is often at the pixel count. So a pixel is a single point or a tennis square in a graphic image. As we discussed, what is a pixel in the last class? A pixel is nothing but it is the minimum, the shortest unit of an pixel. It may be a dot or maybe a square size. It is the smallest element in digital image. It cannot be divided further. So it is the smallest element, like your a point is a smallest element in the your geometric. A line is consist of some points. Similarly, all image it consists of these small elements known as uh, pixels, picture elements. So the resolution of pixel count measurement is quantified as a specific unit of length. The unit is basically measured PPI or DPI, pixel per inch or dots per inch. Although DPI measure accurately refers to the resolution of the device. So that is if more pixels are there per inch, as the name suggests per inch here, the 1 inch square inch, that is the area whose area is 1 square inch, that is 1 inch breadth and 1 inch length. That is the number of pixel contains in it in this area is known as dots per inch. So if the dot per inch is more, if the pixel per inch is more in that area, that is the you will get a better image, because the area is fixed. Square inch is fixed 1 inch length, 1 inch breadth, and it how many pixels, how many dots are present within that area. If the number of pixels is more, if the number of pixel size is less, no, there will be number of pixels and the size is better. If the size of the pixel is greater, if the size is greater, so there will be less number of pixels and the size is poor. Sorry, the quality is poor. The quality is poor because the less number of pixels is there. So here the DPI resolution is associated with the number of pixel within that unit area. Uh, as we already discussed, what is intensity level, what is the gray level value, intensity value. So the intensity is another term like your resolution. It also associated with the image characteristics. Intensity refers to the amount of light or a numerical value of a pixel. A amount of light of a pixel is associated with a numerical value, and that is known as the intensity value of the pixels. Gray level value of the pixels. It is a measure of energy of a wave which is directly proportional to square of the amplitude of the signals. And as we already discussed, this value is nothing but it is a range. For a 8-bit grayscale image, the value in the range is 0 to 255, because there are 256 values, 2 to power 8, 256 values, where 0 represents the black color and the numeric value 255 represent the white color. We have already discussed in the previous class. So a gray level value is, there is a range lies between 0 to 255 for a 8-bit grayscale image, and the 0 represent the black color, whereas the 25 represent the white color. What about the others? What of the other value in between 0 and 255, other than 0 and 255? This is the other values, which is a combination of black and white. That is the pixel value which is nearer to 0 is more darker, more black. But the pixel value which is closer to 255 is more brighter, because 255 is the white color. So the range value is 0 to 255. 0 is a black color, 255 is a white color, and the other values, that is 1 to 254, is combination of black and white. Same thing is written here. You see, the higher value of a pixel is whiter the pixel will appear, because higher value is the whiter, the lower value is the darker, because 0 is darkest and the 255 is brightest. Okay, so if the higher value is, if you are given 2 pixel values, so you compare which one is the greater. So the greater one is the brighter and the lesser one is the darker. You see the same thing written here. The 2 pixel with gray label value 127 and 220. Obviously 127 is darker than the pixel value 220, because 220 is closer to 255 and 127 is closer to 0. So the uh, uh, 127, which is lesser value, is more darker than the 220, which is closer to 255. So if are given two, as I discussed, if two pixel values, So the lesser value is more darker, the greater value is more brighter. So after resolution, intensity, after this, that is another term is associated with the image. It is called constant. The term constant is an image related to according to the difference in the magnitude of the intensity. There are their intensity at the surface of the object. There are many ways in which constant can be measured. It can be described as the product of the sensors signal constants. And this depend on the energy source and physical property of the object, the detector constant. This depends on the way signal detected, captured and stored. You see that is the there is uh, a brightness. It is another terms. It refers to the average pixel intensity of the image. Similar to constant, the image should be reasonably bright to show all the information to the viewer. Excessive brightness may affect the quality. So we need the proper brightness of an image. If the brightness is excessive, the quality is affected. If it is the brightness is very less, also the quality is affected. An image may have a higher brightness, but if the intensity is not optimal, the image again will not be exhibit good quality. So brightness resolution is defined as the number of identified distinct color, and it is also called the color resolution. So another term, which is noise. Uh, it is an unwanted disturbance. We do not need this. We do not want that is noise should be available or present in our image. So noise is an unwanted disturbance that causes fluctuation in pixel value. Such is it is a random of stochastic process, and hence it is true. It is true value cannot be predicted accurately. So, however, noise obeys all the statistic property. There are various process. There are various technique to remove the noise. The noise may be different kinds. Also, we will study in the later slides. What are the types of noise? There are different types of noise. That is this noise affected the value of the pixel. If the value of pixel is affected, if the value of pixel is affected, that is changed, that is the picture will be also you will not get the right pictures, accurate pixel, because the pixel value changes. If the pixel value changes, you will not get the actual pictures. You will get the other pictures other than the original pictures. So the pixel value of a pixel, the intensity value of pixel may be uh, affected by very when you capturing the image. Suppose more brightness comes, so the pixel value changes. If you transmitting an image, when we are transmitting an image, in between the way there are various factor affected uh, the value of the pixel. There may be some external electric field, external magnetic field, and the others wave particles which can be affected by the pixel value. So if the pixel value changes, you will not get the original image of the object. So uh, uh, noise which you don't need. We have already discussed how to convert a signal, analog signal, to digital signals. So here the signal, why the signal? You know that is a wave digital image is consist of signals. That is when you capturing an image, an object, that the lights comes from the air. So a signal is anything you can see, hear, observe, or measure using some machine. You see here, any physical phenomenon that conveys or carries some information can call a signal. Any physical phenomenon which carries some information is called signal. This signal we can see, we can hear, observe, or measure using some machine, that is called a signal. So suppose speech. which are telling speech as a signal, audio is a signal, right? Radio, TV, radar, temperatures, supersonic, ECG, EEG. So all are the example of signals. The information carried by the signal will be function of an independent variable. The independent variable can be time or spatial. Basically, we are associated with the time. So the signal is measured with another variable is known as the time. So the independent variable can be time or spatial coordinate or intensity of color, pressure, temperature. It is so we are basically here the signal is associated with the independent variable time. So the most popular independent, what we are discussing, already discussed that the most popular independent variable of signal is time. So time is uh, uh, the independent variable which is associated with the signal. So here also in our slides, our coming slides, we will discuss that is the signals with respect to time. So, depending on the number of a variable, a signal can be classified one dimensional or multi-dimensional. You can also two dimensional or multi-dimensional. A signal which is a function of a single independent variable is called one-dimensional signal. Music, speech, heartbeat. So these are the uh, uh, in one-dimensional. A signal with the function of two or more independent variable is called multi-dimensional. A photograph is example of two-dimensional element. The image we are discussing. Our topic is digital image processing. The image is a two-dimensional signal. From the first class, we have already known that the image is a two-dimensional signal. Always two-dimensional. One the location, another is its value, corresponding value, intensity value. So the a photograph and image is always a two-dimensional example. So a one-dimensional signal is a function of a single variable. We have already discussed which represent a function t. So one-dimensional audio signal such as the electrical signal at the output of microphone is a function of a time. A two-dimensional element we already discussed. We are interested in this a two-dimensional signal because our image is a two-dimensional signal xy and f of xy. Xy is a function of two independent variable x and y such that xy indicate the point of 2D. For example, if the function shows the intensity in a still image that f of xy represent the value of intensity for the pixel of the location xy. So that is why the image we are discussing is a two-dimensional signal. One is xy, another is f of xy. We have already discussed in the last class. From the very beginning, we have already discussed a digital image, nothing but it is a two-dimensional, that is contains two component xy its location and f of xy the intensity value, the gray level value of that pixel of that location. Xy f of xy. Uh, a grayscale image is a discrete 2D signal. If xy having two independent variable and fxy we have already discussed whose location in the image is given by integers x and y. The 2D signal can be various types of that separable periodic it is. Therefore, the 2D signal represents a digital image where the xy is the location and fxy is the value of the picture. We already discussed. Uh, अच्छा. Then, transformation. What do you need by transformation? The what does the mean? What does the word transforms mean? The transform means that is convert from one form to another. That is convert from one form to another. That is called your transformation. Here we are transformation of 2D signal. So why do we need a transformation? We'll discuss later how the transformation is done. But the question may arise in your mind that why transformation? Why we required to convert from one form to another form? You take a simple example. Our slide also there. We'll discuss about that. The transformation of a signal fx will convert to a signal into a new signal gy in different domain. However, transformation does not change the information content. That is after contents uh, does not information content present in the signal. So if you make transformation, so that the signal will be lost. There is no useless. This is useless. So after transformation, the signal will not be changed. That the information should be preserved. So why do we need transformation? My question was, why do we need transformation? You come to the next slides. You see here. Forget about the image transformation. You see, there is a change in problem representation can help to solve the problem fast. Suppose there is a Roman form. There is a Roman form. X double I 12 into X is 10. So if the question is given that X double I and into X, you have to convert this to your numeric system, where general numeric system or Arabic numerical system. And once it is converted, x double I to 12 and x to 10, we can multiply easily. 10 into 12 is 120. Otherwise, if you don't know the x double I is 12 and x is 10, if you don't transform it or convert it, it is not easy to multiply. So x double I, we know that x double I is 12, x is 10, and we multiply it. The multiplication, the result is 120. So for easier calculation, for easy calculation to convert this. So this is transformation. Come to the last second example. 12,000 into 15,000. So if the multiplication value also, if we multiply this, it will be take more times. But if we convert to polynomial form, to the mantissa form, exponent form, 10 into 12, 23 plus 15 into 10, 23. So it can be stored easily. So you know that floating point representation. You recall the floating point representation. That is a large number can be saved in a computer memory using floating point notation. There are various techniques. There is single precious system, double precious system. There are some mantissa. There are some exponent. Mantissa is stored in one format. Exponent is stored in one format. So we need to convert. Otherwise, a large number cannot be easily stored in a computer memory. So that is why there is a floating point representation to store a large number. So a large number can be converted, can be transferred from to the exponent and mantissa form, to the scientific notation form, to polynomial form. After that, it can be calculated easily. It can be stored in computer memory easily. So this transformation make our work easier. So if we don't transform it and want to preserve its original form, it is difficult to multiply and it's difficult to store. So that is why the transformation is required. Exactly from the same reason, in the image processing, the transformation is required. because suppose your image is in one domain, it not be suitable for processing. It may not be possible for editing. It may not be possible for getting information exactly, the exact information from it. So that is why we have to convert to the another domain. That is called the transformation. That is called the transformation. Uh, Intensity profile. As we discuss, the intensity is nothing but it is a numerical value of every pixel. Every pixel has a numerical value that is called the intensity values, gray label values. Sometimes in some books it is written as tone value, tone, T-O-N-E, tone values. Are you getting something from this picture? No. I have written here they are W and B. You see, in red color I have written they are W and B, white and black colors. You see the first. You see the original image. First is white. You see that is the graph is in the peak top. Second is black. That is the graph gradually decreases. Richest is minimum value at B 0, and again there is a white color. White color is 255 maximum. So then it is gradually increases. Richest is maximum value W, where the W is written, and after that there is another black color, so it is gradually increases. You see the intensity, the black color, then actually the color is darker, then it is, so that is why it is increases. Richest it is 0, and you will get the similar pattern. And you see there are 4 peak values and there are 4 minimum values. There is also in the original image the black color like your cylinder, 4 black cylinder like, and white cylinders, and this graph is no, is nothing but it is called the image profile. That is, from the image profile you have some idea about the gray label value, intensity value uh, of an image. It is called the image profile and or intensity profile. That is, from this graph we will get some idea that that is the what is the pixel value of that image. There's a graphical representation of the intensity of the intensity value or gray label value of each pixels, and we will get some idea that that is this is the intensity value of that image. And this graphical representation of an image is known as image profile or intensity profile, and it is very required, useful in image processing. It is very useful in image processing. So please write your name and registration number in the board. Do not repeat. Those who have not written, please write. The term frequency is for the rate of repetition of signal in spatial domain f is equal to 1 by t. Spatial frequency is used to describe the rate of change of pixel intensity of an image in space. We know that f is equal to 1 by t. It can be visualized using the profile of the image in a row or column. So you can show, we have already showed in a row and column. This is a graphical form. There is a x-axis, y-axis. X-axis represent the distance of the pixels and y-axis represent the gray level. We have already discussed in the pixel profile in the previous example. So it can be written, it can be shown, it can be represented using a graph, x-axis and y-axis. So it is x-axis represent the distance, and where y-axis represent the gray level value. Image transformation orthogonals. So as you know, and what is transformation? Why need you transformation? So transformation is nothing but it is a convert convert a signal or a image from one domain to another, one form to another. Why we need it? Suppose the original form is not suitable for image processing, for getting more information. So we need to transform to other form, and this transformation can be done using a mathematical function known as transformation function. We have, you see, there is a mathematically formula written for transformation and inverse transformation. The forward and inverse transforms are opposite to each other. If we apply the forward transformation, the image convert from original to another form. If we apply the inverse transformation, as the name suggests, it is, we have to convert that new form to the original form. Suppose we are converting from form A to form B using forward transformation. Similarly, using inverse transformation, we will get from B to A. From B to A. A is original form. So this is the formula GUV TUVXY into f of xy. TUVXY, what it is a mathematical function known as transform function. Into f of xy, its gray level value. Similarly, we will f of xy is original value. Similarly, using the inverse transformation, we will get f of xy from the GUV. GUV the new form after applying forward transformation, and effect and your inverse transformation exactly works opposite to the forward transformation. It will return you the original form. You see here, fx, you will get the fxy. The original is fxy, where ixyuv into guv your transform form. तो GUV से भी हम fxy will get that. हम original हमको मिल सकता है. So here TUVXY is known as forward, and IXIUV is known as the inverse transformation. In previous example, you see we are using TUVXY, which is known as the forward transform function, IXIUV, which contain the inverse transformation function, and both are opposite to each other. Inverse transformation, kernel separability. So transformation have some important property. Kernel is called separable. If TUVXY is equal to TUX and VY, kernel is called symmetric if TUX and T2V. So these are two property, and it is known as the kernel. Let us take a good example. This may be important to find the forward transformation. This. Is it visible? Please zoom it. So it is a handwritten slide. It is not clear. So we may zoom it. Is it visible? You see there's a f whose intended value is given. Uh, 2221 is the original image whose value is given, whose gray level value is given in rows and column wise. As you discussed, the value is given in the rows and column wise 2221. So the forward transformation is given by the function a into f into a. So g equal to a into f into, so that is the forward transform function is a into f into a. What is a? 1 by root n m pq or eq, that is minus of that matrix. Please remember minor the cofactor of matrix. Matrix multiplication, matrix cofactors, matrix adjacency, matrix transpose. So 1 by root 2 and 1 1 1 minus 1. So g is equal to a into f into a. A is equal to 1 by root 2 1 1 1 minus 1. F is equal to 2 2 2 1 is already given, and again a is 1 1 1 1 minus 1 1 by root 2. 1 by root n is here the order. So I am multiplying 1 by root 2 into 1 by root 2, which was outside of the 3 matrix. That is 1 by 2. Now I am multiplying the first matrix and second matrix. 1 into 2 plus 2 into 1, 4. Please recall the process of matrix multiplication. So if you get row wise in the first column, first matrix, and the column wise in the second matrix, 1 into 2 plus 1 into 2, 2 plus 2, 4. Similarly, the first row and second column, 1 into 2, 2 plus 1 into 1, 2, 3. Similarly, the second row and first column, 1 into 1, 1 into 2, 2 plus minus 1 into 2, minus 2, 2 minus 2, 0. And then the second row and second column, 1 into 2, 2 plus minus 1, 1, 2 minus 1, 1, minus 1. So 2 minus 1 plus 1. So the multiplication of the first and second matrix is 4, 3 and 0, 1. Now I am multiplying this result, that is the multiplication of first two matrix with the third matrix. That is 4 into 1 plus 3 into 1, 7. You see the 7. Then 4 into 4 into 3 minus 1. And 0 into 7 plus 1 into 1, 1. And 0 into 1 plus 1 into minus 1, minus 1. So finally, we will get g is equal to 1 by 2, 7, 1, 1 minus 1. So this is my transformation. The new value of this image is new gray label value is 7. 7 by 2. If we multiply half into each element, 7 by 2, 1 by 2, 1 by 2 minus 1 by 2. So this is the forward transformation. After forward transformation, we get a new value of g, new value of x, which is g. So you see, the f and g are different. So f is the original gray level values, 2, 2, 2, 1, and the new value will get 7 by 2, 1 by 2, 1 by 2, and minus 1 by 2. So let us make it forward information, inverse. You see, in inverse transformation, we'll get f equal to same. We're multiplying a inverse with g, because we multiplied a to get g, a into f into a. So to get g f again, to get the original value, we have to multiply with a inverse. So a inverse into g into a inverse. So a inverse is equal to 1 by root 2 1 1, because it is a 2 cross matrix. You can easily find the a inverse. Otherwise, you can use the formula adjacent a by determinant a and get the inverse of a matrix. And you will get the a inverse is equal to 1 by 2 1 1 1 minus 1, the same as the original matrix. So now f is equal to 1 by root 2 a inverse into g into again a inverse. So 1 by root 2 into 1 by 2, 1 by root 2 equal to 1 by 4. Multipliers of two matrix, first two matrix is 1 into 7, 1 into 1, 8. Similarly, first row, second column, 0, 1 into 1, plus 1 into minus 1, 1 minus 1, 0. Similarly, second row, first column, 1 into 7, 7, minus 1 into 1, 8. Uh, Similarly, second row, first column, 1 into 7 into minus 1 into 7, then 1 into 1, minus 1 into 1, 2. So we will get, if we multiply each term, 8 0, that is minus 8, minus 7 minus 1, minus 6 is the written is as mistake. 8 0 minus 8 0, 8 0 8 2, 8 0, sorry, 8 0 8 2. So if we dividing it by 1 by 4, we will get 2 2 2 1. That is, you will see, we will get its original form again. That is, using the inverse transformation, we will get f 2 2 2 1, which is originally 2 2 2 1. So this is the your transformation function. We am using t uvxy and ixy uv. So applying the forward transformation, we will get g, and using the inverse transformation, we will get f again. So that is your inverse transformation, and forward transformation works opposite to each other. Then the next term is image enhancement. Image enhancement technique improve the quality of image by perceived by human observer or machine visual system. As the name suggests, enhancement. So we are enhancing here the quality. improve the quality, which is observed by the any machine vision system or human observer. That is, whatever the quality of the image, but if you enhance its quality so that it is observed by a machine or human easily, that is known as image enhancement. It improves the perception of information in an image for human viewing and provide better input for other automation image processing techniques. Suppose from you are giving a input to this image to another machine vision system, so the input should be better. If the input is better, you will get a better output. If the input is not better, that is, if it's worse, so you will get a you will not get a right or your required output. The main objective here is we have to modify some attribute on image to make it more suitable for given task or specific observer. We have to modify the attribute of the image to get it a better quality image. Some attribute we have to modify. We know that what are the attributes of the image. We have to modify that attribute to get a better image. Suppose some part is not visible of an image, some part is some pixel is not clear, some picture is spurious, and so that we have to modify that picture value, the pixel value of that point. Uh, no, that is called your image enhancement. So uh, the main aim of the image enhancement is to improve the picture quality so that it is easily observed or observed by a human or a machine. There are broadly classified into two categories. The enhancement is spatial domain method and frequency domain method. In partial domain method, pixel values are manipulated directly to get enhanced image. Whereas the frequency domain method, firstly, some transformation is required, and after that, the enhanced technique is used. So in partial method, the pixel value are directly modified. We have some example we'll discuss. But in frequency domain, we have to first transform because the frequency domain directive cannot edit the manipulate the pixel value. We have to uh, transform it. So that is why we already discussed what is transformation. So in partial domain, in frequency domain, we cannot modify the pixel value, manipulate the pixel value directly. So that is why the transformation is required. Then the Fourier transform is manipulated and the modified spectrum. We will discuss about the Fourier transformation. Like your previous example, 1 over transformation is given that 1 by root 10 into A into A. So there is a Fourier transform is manipulated and the modified spectrum is transformed back to the spatial domain using the view enhancement. So once it transform, after that the inverse transform is used to get the original form. So the image may not be manipulated directly. So that is why we have to transform using Fourier transform. So after once it is converted, now it is easily be manipulated. After manipulating, we have to convert again to its original form using inverse Fourier transform. Let us discuss some example. Of partial domain enhancement and frequency domain enhancement. So as we know, in partial domain, the pixel value are directly manipulated. We need not to perform any transform. We need not do here any transformation. The gray label value is directly manipulated. Such operation simply take the gray value of the each pixel or neighboring pixel, map it to new value, and move on to the next pixel. This is easily. You can the partial domain is easy because we need not do any transformation. We need not to convert the picture from one domain to another domain. We can easily modify or manipulate the gray label values of an image directly. So uh, let us see how. Let us fxy is the input image. An image process operation in spatial domain may be expressed the mathematical function t of fxy applied to the image to produce a new image GUV. Therefore, gxy is equal to t of fxy. So we will get a new value after manipulating the gray label value directly. We need not do any transformation. So image enhancement is this is that there are two type of image enhancement. One is spatial domain and frequency domain. Constant stretching is another uh, part of the image enhancement. Constant C between two labels x1 and x2 are defined as the absolute value of the difference between x1 and x2. So x1 minus x2, its absolute value is nothing but it is C of xy x2. So good constant is an image is important to distinguish the detail, else they will emerge in background. So low constant image occur due to bad or non-uniform illumination of condition or due to non-equality of image acquisition. So we will discuss that is the constant is also associated with the quality of an image, constant brightness, resolution. So the main idea to reduce the low level gray values is to increase the mid-range gray values. That is, if there are some pixels which have low level gray values, so we have to increase it. We have to manipulate it to the mid-range gray values, so that an artificial constant is created between the two set of the gray values. The constant between gray values are thus traced from both sides. Okay, if a particular pixel value has having the low level gray values, we have to increase it to the mid range. Mid range means that is you know that it is 0 to 255. So mid range is around 127, 128. So 128 is known as the mid value. So we have to increase that value up to the mid values. Okay, so that the constant between the gray values is thus traced from both sides. So both sides it is traced and it cannot be uh, avoided in a background. It cannot be seen. So you can avoid that by using stretching its constant. So it is called the constant stretch. How to stretch? You have to manipulate the low level values to the middle range values. Let us take an example. A better example is there. We'll discuss about that. You see here. Okay, this example. Before that, we have got to some mathematical transformation is there. Here you see here. So this need a transformation. Alpha r and r lies between 0 to a. We'll discuss what is a and b. Alpha, beta, gamma are slope of the different regions. The slope determines the around of constant stretching. This constant stretching we have discussed. This is depend upon the slopes. If the slope is greater than 1, the corresponding gray label or stretch are increased because the is greater than 1, the slope is greater than 1. If it is less than 1 or smaller than 1, the constant is diminished. So a slope of 1 indicate that there is no change. So the parameter of AB are user defined. So let us come take some example. So there are two types of technique used for these purposes. One is clipping, another is threading. The clipping is this operation stretches the constant to the maximum value in the limit range 0. Original gray level value A to B, but we have to convert it to its maximum value. All the gray label outside this window are either mapped to 0 or maximum value. It is either black or white. There is no other values. The clipping allows us to focus all the available constant onto the required range of the gray label values. This is an easily useful when viewing medical image such as CT image, CT scan image. So CT scan image is an example of a clipping values. That is which is either 0, black or white color. Similarly, thresholding. This is only two values are present in the image. A suitable threshold value is there. T. All the gray labels smaller than T are mapped to 0, or all other value greater than T is mapped to the maximum value 100, 256 or 255. This is the very useful operation in image processing application. Binarization is generally done before segmentation. You see here, this is the image. You will get more clear about that. You see here. Here you see the original image and its FXY in the matrix form 0, 10, 50, 100, 5, 95, 150, 200, 110, 150, 190, 210, 175, 210, 255, 100. So this picture have different gray label values. It gives the example of some pixel, not all the pixel on the image, some pixel is given. So this is your image profile, intensity profile of the image, and the threshold value is taken as 128. You can take any threshold value, 110 or 120 is given here. And the idea is any pixel value less than 128 is mapped to 0. And any pixel value greater than 128 is mapped to maximum 255. You see here, 0 is mapped to 0, 10 is mapped to 0, 50 is mapped to 0 because it is less than 128. 100 is also mapped to 0, 5 is mapped to 0, 95 is mapped to 0, but 150, you see 150, the corresponding 150 value is 255 because it is greater than 128. So any value is greater than 128 is mapped to the maximum, or any other value which is less than 128 is mapped to the minimum value 0. That means you will get either black color or white color in the image. You see the example in B, the resultant image in B. It is a black and white color. No other value is allowed. No other value in the setting. Are you getting?
Yes, sir.
So it is easily be understood. So the zero value, any value less than 128 is mapped to zero, black color, and any other value which is greater than 125, it is thresholding, and it is converted to 255 to white color. So this is the effect of thresholding. You have to take a threshold value. Here I have taken t equal to 128. Similarly, clipping. Clipping, you have to take a middle value. You see here, the constant stretching, the slope is here greater than 1, it is called clipping. Constant stretching, that is the quality is enhanced. There is a low constant image. So after constant stretching, you see we got a better quality. So constant stretching is a technique to enhance the quality of an image. Then digital negative. There's an option to get this digital negative in your phone. You can find the digital negative on any image of your uh, any image stored in your computer memory or your phone memory. So there's an option in your camera section to get the negative digital negative. Most of the smartphone have this option. You may get it. That is, as the name suggests, negatives. The pixel value are uh, negated. Negated in the sense 0 become 255, 255 become 0. That is, black color become white, white color will become black. Similarly, the 10, the gray label value 10 will be converted to 255 minus 10. 10 is the darker, 10 darker because it is nearer to 0. But 255 minus 10, 245. 240, that is 10 is replaced by 245 pixel value. So the digital negative, as we discussed, that is it negate, it is a complement of the pixel value. Subtracting from the pixel value from its maximum value. You see here the digital negative on image with the intensity level of the image 0 into n minus 1 is generated by using negative transformation, which is given by the expression h is equal to l minus 1 minus r. Suppose r is equal to 10, s will be 255 minus 10. Here maximum is 256 minus 1, 255. So 255 minus 10, 245. So the pixel value of 10 is negative. Its digital negative value is 245. The digital negative value of 0 is 255. 1 is 254. 2 is 250 and so on. And the digital negative value of 100 is 255 minus 100, 155. Let us see. So here S is 255 minus R. So if R is 20, 20 is a dark pixel. So because 20 is nearer to 0, 20 is a dark pixel. What we will get S is 255 minus 20, 235, which is a bright pixel. 235 is closer to 255. So 235 is a bright pixel, as compared to 20. So the negative value of 20 equal to 235. Similarly, if R is equal to 125, S is equal to 130, 255 minus 125. So that middle gray label has not changed much, whereas dark label change. So middle value does not change much because you see here R is 125, S is equal to 130. So 125 and 135 almost look like same, because they are called the middle values. So 125 is close to 128, 130 also close to 128. So you cannot distinguish larger. They are same. So the middle gray level has not changed much, whereas dark level has become bright. Zero is become 255. Zero is purely black, totally black, maximum darkest, and its negative value 255 is brightest. You will get the significant difference. But in case of 125, you will not get the significant difference. Because 125, 130, almost same gray level values, and almost look like same. The transformation is generally used to enhance the white details embedded in the dark region or an image where the black is dominant. It is useful to display the medical images shown in the example. Even though the visual contact of both images are same, it is much easier to analyze image negative form. You see here the image, which is white color, here is black color. You see the border. The border of the original image is totally white in original image, and but the border of the your digital negative form in B, it is black. And you also find the pixel which are darker in first image is brighter in second image. So you see here, find the image negative to easily be calculated. 0 255, 10 245, 50 205, 100 is 155, subtracting from 255. Each pixel value gxy is formed by subtracting each pixel value 255. So this is a image negative transformation. Intensity label slicing. A variant, this is also a part of the thresholding, a variant of thresholding is intensity label slicing or double thresholding. We have already discussed the thresholding. Thresholding means that is you have to convert either 0 to minimum or maximum 0 or 255. So it is known as the intensity label slicing or double thresholding. Let us see what is double thresholding. It is used to highlight a range of intensity value of a interest in an image. That is, in this operation, all the gray label in a window A to B. In a window A to B, there is a range are set to be maximum gray label. If the pixel label values is lies between this window is set to maximum label 255. All the other gray label value which outside of the range is set to 0. Please recall what is the single thresholding. If all the value is threshold value 128 is less than that, it's set to 0. Which is greater than 128 is set to 255. But here is the difference. We have to select not a one value, a 128 threshold value, a range. Suppose 100 to 150. Suppose 150 to 150. If the value lies between this, it is range to it is mapped to 255, otherwise to 0. So this is called the intended label slicing or double thresholding. You may get a question, what is the thresholding and double thresholding? It is also a binarization because you will get two values, 0 or 1 or 0 or 255, black and white. The resulting image has only two gray label values, 0 and M. Mostly this technique is used to remove unwanted element from an image so that the useful information becomes prominent. Applications are enhancing certain features which are based upon the gray label values, such as mass of the water in satellite image, cancer cells in monogram image. So you have to set a window, set a range here. So you have only interested in the some part of the image. You can enhance the image of that part using this double thresholding. Suppose you are only want to see the mass of water in a satellite image. The satellite image may contains uh, many information, but you are interested in your mass of water there. Similarly, suppose a monogram image, you are only interested to see the cancer cells. A doctor is interested to see only cancer cells, the intensity of the cancer cells. So they can use in double thresholding. At the name search filtering, we have to filter here, remove here the unwanted component or a small detail in an image. Suppose some components does not contain any noise or any component which are not useful. So we have to remove by using filtering. In digital image processing, filter is basically sub image and is known by various names such as mask, kernel, template, or window. Filter can be two types, partial filter and frequency domain filter. Partial filtering. One of the main tools used in variety of applications such as noise removal, bridging the gaps in object boundaries, and sharpening the edge. So the partial filtering is used for these purposes in noise removal or bridging the gaps. Suppose there is some gap in between your pixels, some pixel value is missing. So we have to fill it. We have to fill it by a suitable pixel having suitable gray level values and object boundaries and sharpening up gap in object boundaries and sharpening the edges. Sometimes some edges are uh, uh, misleaded or there is some boundary problem, that is some boundary is not viewed properly the border of the image, so it is also used for sharpening that. The idea of spatial filtering is to move a mask, a square of odd size, either 3 cross 3 or 5 cross 5, 7 cross 7 over a whole image pixel by pixel. So 3 cross 3 means 9 pixels. So we have to examine any 9 pixel at one go. First 9 pixel, then 9 pixel, then 9 pixels, and at last we will cover all the pixel of an image. Similarly, if the mask size is 5 cross 5, we have to examine 5 into 5, 25 pixel in one go. At each pixel, the corresponding value of the mask and the image are multiplied and added up to replace the original gray values of the pixels. This process is known as convolution. So by using the convolution, uh, we can uh, change the pixel size or pixel value. If some pixel is missing, if there's some breach of or gaps in the object boundary, or some edges are not sharpening, so we have to use the convolution method. So sometime you will get a question, what is convolution? So convolution nothing but the the pixel value is manipulated by using some techniques. Some pixel value is multiplied and added to replace the original grade values. Suppose a particular pixel has the spurious grade level values, we have to modify it. That is called the convolution. You see here, we'll discuss about the process. You see here, a pixel at position xy, suppose we have to change that value. Suppose this pixel having, I think that is this pixel having some spurious values. This pixel is missing, or this pixel value is contains some noise. Some part, this part contains some noise, and this is some pixels. So I have to take a mass of 5 cross 5. It is not given that 5 cross 3 is there, but actually take 5 cross 5 or 3 cross 3 or 5 cross 5, and that pixel which is labeled in some gray color, you see, suppose it has some noise. So we have to filter it. How to filter, we'll discuss. How to filter, there are some process, we'll discuss about that, but we filter it. And we filter that, after we filter, we get the original pixel, you see. You will find the image after filtering. So the pixel which was spurious, which value is contains some noise, or suppose this value is gap, now it is filled. So what is the process? Now we create a new image where gray label values of the pixel are calculated from the values under the mask. We have taken mask 5 plus 5 mask, and the gray label values of that pixel is calculated, changed. So the values under the mask are modified by a function called filter. Sometimes it is called filter function. And by using the filter function, the have been modified. You already see in the previous slide, the pixel, the value of the pixel is modified. That is why it is seems more darker than the original one. Obviously, it is modified by using some function. Something is added. Something we will discuss about that. The median filter after these slides, how it is modified. How do it modified? What is the function used here? There are various techniques to modify this. Our later slides will discuss that. So values under mask are modified by a function called filter. If the filter function is a linear function of all grade level values in the mask, then filter is called linear filter. Else it is called non-linear filter. Filter. If the filter is a linear filter, if the filter function is a grade level values of the mask, it is a linear function. It is a simple function, general functions. So it is a linear filter. Else it is called non-linear filter. Basically, you use a linear filter. So types, smoothing is happening, and this is the process. This is the steps of filtering, and the next slides contain some masks, and this is the gray level values, and okay. So no, you can ask now any queries. I've already sent the slides. Please go through it. Please go through it, and you can, if any doubt comes, you can ask me. If you have any doubt. Are you actually aware of that? That is some assignment markers not calculated or not seen. So you have there's just also this problem in your next the previous batch. Some students complain that the in previous batch that their assignment marker not there. They they face some problem in assignment marks and projects.
Sir, where I will find this slide you have shared?
I have already sent in the group. You have
Actually,
added me in a group in last class. Are you there?
no, I am not in the group actually.
Oh, what's your name?
Samir Kumar Mandal.
Samil, you may write your email ID
Okay.
in the board. Okay,
Hmm.
so that I will send to individually. But I have already added by someone
Okay.
in the previous group. I have shared that my slide in that group. If are
Okay.
not
So
there,
I am sharing my email ID here. So can you please
I
add
will
me?
send that. Okay,
Yes. Yes.
those who are not in the group, please share your email IDs so that I will send you individually.
Okay, sir. I have sent already. Please check.
Okay, okay. Write your email ID there. And
Sure.
those in the group, no problem. Those who are not in the group. So we'll start in the next class from these slides.